అయింది అది సార్దా మందలేదా ఇక్కడ ఓ పర్లేదు నాదైనా ఆయనకి ఇచ్చేయండి ఆయనదైతే ఆయనకి ఇచ్చేయండి నాది ఉంది నాది So, good evening. So, I am not a material scientist, nor a metallurgist. I am a mechanical engineer. Yeah, it is very tough after Chenapat lecture. My talk will be something related to design aspects, nothing to do with microstructure or the modeling part. So my talk will be basically on the design considerations and guidelines in additive manufacturing. Yeah, we have enough introduction to additive manufacturing, so let us try to restrict the introduction part as crisp as possible. And here the coin word is a design. So why design is so important in additive manufacturing is the conventional design is not taken here for additive manufacturing. So we'll try to see is there any approaches, design approaches, various design approaches in additive manufacturing. So yeah, that is one of the topics which I'm going to discuss. And additive manufacturing, you have a unique capabilities, right? So one among is the topology optimization, where you can optimize the structures, you can make a lightweighted structures, and we can biomimic say the designs or the structures where you are going to mimic the biological aspects or from the nature we can inspire, the designer can inspire, but now artificial intelligence, right? So you have AI inspired designs, right? So which it can be. So one can understand these designs once it has been inspired from the nature or the biological inspiration. Obviously, it is very complex, right? So the complexity is a free of cost in additive manufacturing. So then you see these topology optimized structures or bionic designs. So we'll try to see how it is getting connected to AM, of course. And AM processes, yes, the previous speaker has given enough introduction or the working principles of AM. And another advantage or unique capability of additive manufacturing is part consolidation, which we have seen one of the case study from the GE. So that is, say, LEAP engine, fuel nozzle, right? So where you can consolidate several parts in an assembly or in a sub-assembly. So but definitely if that is the case, then we need to see the guidelines or we need to know the constraints of each and every process, right? Say each process, it will have its own constraints or in terms of minimum size of the feature that you can produce out of 7 AM processes, it's not same, one to other it will vary, right? So then we'll try to see some design guidelines in part consolidation kind of philosophy. And another one is a tooling area, right? So you have, say, injection molding. So injection molding dies. So where you can make a conformal cooling channels here with additive. So we'll try to see some of the design guidelines for in tool making or in designing the conformal cooling channels. We'll try to see some of the guidelines. And of course, the polymer, which the physics behind or the interaction with the material against the energy source is of course different in polymer versus metal, right? And we have enough on the metal side. Then we'll try to see some of the design rules for polymer as well as metal. And finally, build simulation. Of course, this workshop itself is for the simulation and modeling. So then we'll try to see, there are several challenges. It's not that much easy. Then we have to appreciate the expert, like how much, say, effort you put in, right? So, and still we cannot find a proprietary software which you can, we have seen several challenges which he has been explaining through his lectures, right? So we'll try to see the challenges and the build simulation scenarios, right? So this is what my presentation goes, maybe another 1 hour or 1 hour 15 minutes. Yeah, of course, as we are migrating from industry 1 to industry 4, in fact, industry 5 right now. So the transition time is very less. Now the technology is growing very fast, right? If you try to see the time scale from 1 to 2, so it may be 70 years or 80, 90 years, and similarly 2 to 3. But 3 to 4, it may be 10 years or 15 years. Even 4 to 5, it is very less, right? So then one can understand the technological the advancements or the how your technologies got evolved, right? So then you are very much aware of the technologies like autonomous systems, cloud computing, system integration, simulation, IoT, augmented reality, digital data, big data analytics, cyber security, right? And then coming to the manufacturing scenario, so undoubtedly the additive manufacturing is going to play a major role in the current industrial revolution, maybe 4 or 5, whichever you call that. But the additive is going to play a major role. Even a lot of statistics and surveys are saying that additive manufacturing is going to play a major role. If you try to see the cumulative annual growth of this manufacturing, especially additive manufacturing, it's in a huge numbers, right? So then one can understand the importance of this technology. But this is not a new technology, as we know that it has started with the name called rapid prototyping, that is during late 80s or early 90s, right? And now it may be matured to a manufacturing, that's what you may be renaming, or you may be calling that as additive manufacturing, or in a in a more common name, it may be a 3D printing, right? So, but the essence is same, like you start with the digital data, where you maybe CAD data, maybe 3D digitized data, right? Or it may be a CT MRI in case of medical. So your digital data is the input, and where you can say from digital data to physical component or the part or assembly. Now pin to plane, you could able to make it with the additive manufacturing, right? So yeah, and this is also the previous speaker has given very elaborately coming to the traditional manufacturing, like subtractive. You have a concern about the scrap and the complexity, the product complexity, right? So this is very simple. It's a flat geometry. You don't much worry about subtractive if this is the kind of geometry. But if you change a geometry from this to a free-form coffee cup, something like this, so then we need to see several constraints here. So right. But if you have another hand, you have additive manufacturing technology. So always you work with a 2.5D dimension always, right? With a 2 dimension with a uniform thickness. So your complexity always, you never work a 3D complexity in 3D printing or additive manufacturing. Always you work 2.5D complexity with a uniform thickness, right? So that's what, but in case of traditional manufacturing, always you may work with a 3-dimensional, so instead of that, your complexity has been reduced, or rather than always you are working with a 2.5D dimension, right? And you have other concerns, whatever we have in a subtractive. So those are eliminated here, right? But you have another challenges in additive, which we are, and formative, the same case, like for in case of say molding or say we need to make a die or a mold, and then again, how do you make this die or a mold? So again, you may go to the subtractive, and then the same story will repeat. But anyway, so the additive, yeah. So then, cost per part versus number of parts. Obviously, the break even, like where you can see, yeah, this is where AM or 3D printing is not meant for mass production, but it's very good for mass customization, right? You know what I mean by a mass customization, right? So that is the buzzword in Industry 4 or even in fact Industry 5. So the mass customization, so each part is unique. Each part is different geometry, different dimension. So in that case, now I will put in this manufacturing cost versus complexity now, right? So the complexity is, say, increased in a conventional manufacturing process. Your cost is also exponentially increased. So it is a quite reverse scenario, the previous graph and this graph. So your complexity is something like, it is very less complex, right? Always you have a circular, cylindrical kind of a features, but your designer has changed this design to a bio-inspired or to a topology optimized structure, right? So means your complexity, if you see this is a 1x complex, it may be a 5x or 6x complex. So then your cost is also now, it may be a 5x or it may be a 10x if you manufacture through a conventional method, right? But your additive is a guy which always remains constant, right? So irrespective of your complexity, so your cost remains same. That's what this guy is winner here. So is it only the cost? So not only cost, if you try to see the conformal cooling channel which we are talking about, so the performance of the system, right? You have the tool life, or you have the errors here in the solidification errors in case of traditional cooling channels versus your conformal cooling channels, so where your die life has been increased, right? So all that means not only the cost reduction in terms of additive, so it will add the value to the product or the component in terms of increasing the performance of the system, right? So in case here is the die cycle time, even also it has been reduced here, the traditional tooling versus conformal cooling channel. So your performance of the system has been increased. So that is another advantage which you are going to get out of this technology, right? So you have the cost to benefit as well as the performance or the efficiency of the system has been increased once you migrate to additive manufacturing. Yeah, of course, if you want to take a decision, then obviously your additive or 3D printing, so you come whenever you have a highly complex product, right? So, but that is in a limited quantity, maybe a dozen or maybe a few dozens, but not more than that. But always you look for or apt or select this 3D printing additive manufacturing whenever you have a highly complex product, right? And you have a medium complexity and medium quantity, of course CNC is the right choice. And if you have a lower complexity and at the higher quantity, right, and then investment costing, but medium complexity and higher quantity, then you can go with the injection molding, right? So typically, what is the moral of the story? 3D printing or additive manufacturing. So definitely, it is, you can justify whenever you have highly complex and relatively less number. So yeah, and these are the various steps involved in any typical additive manufacturing system. You start with the CAD model, right, and then convert as STL file, and then where you have interfacing software with the machine, then you transfer this data to that software, which is say the interface with the machine. Then you do all the slicing, the laser strategy or layer thickness or whatever process parameters. You set it here. If not, the software will automatically take some default parameters and it will generate a machine setup or rather than the code. So that code will be sent to the machine and physically layer upon other layer. So which your part from the first layer to the last layer, it is getting fabricated. And then you unload the part, remove the part. So you have the supports and you have a loose powder in case of a powder based feedstock you are using it. So you do that, you remove the part, and now you do the post-processing. Now, you are not satisfied with the mechanical properties or microstructural thing which you want to improve it, right? So, obviously, as built versus your post-processed component. Why? Because your application demands, right? So, based on the application, even your post-processing, like it can be a heat treatment, so it can be any surface treatment or heat treatment or hipping. So you can do perform several post-processing methods, maybe the application, based on the application, and as you are not satisfied with the as-built component properties, then obviously you may go with some post-processing techniques to adopt on it, right? So this is a complete value chain. So you have a design engineer, you generate the CAD model, and then you obtain the CAD and do analyze the model, right? Means maybe you want to do some perform topology optimization, right? You want to redesign. Why? Because, yeah, it is very much needed. Then very soon we'll discuss why you want to redesign always or reimagine your designers, say, and then why you want to come out with altogether a fresh design. Why not the traditional or the conventional designs are not, say, carried to additive manufacturing? So then we need to do some sort of topology or lattice design or some sort of bio-inspired designs. So then we do that and generate the test-related model, that is STL, or it may be AMF, 3MF, right, or OBJ. So you have a test-related data and you generate the build model, right? So then anyway, I'm not going to touch up these process plan. Maybe during the lab sessions, maybe Uday and the Srikanth is going to talk about, like, how do you set up all these in a 3D expert software, that is with the metal AM. We are going to have a lab practice on this. And once you do that, so you generate the build model, right? And then you prepare the machine, right? So you start the machine. So you have a machine operator. So and then start the machine. So that preparation of the machine is over and manufacture the part. So whatever you have, say, virtually you have done all these parameter setting and generating the code. Now physically it is getting realized here in the machine. And even we need to check with a kind of, you have a manufacturing engineer here, so where you obtain the manufacturing part, like say where you need to, say for example, you have the recycling of the powder if it is a powder based system, right? So the manufacturing engineer will come into picture and do all that. And then you have, say, the post-processing of the part, just now we have discussed. So the post-processing, which also covers right from the removing the supports, enhancing the properties, just now we have discussed. It may be through hipping or annealing, or maybe you're not satisfied with the accuracy, then sometimes it may be subjected to machining, and sometimes it may be a chemical polishing and surface texturing, right? So nowadays you have even short peening, milling, grinding, sanding, polishing, abrasive blasting. You have the post-processing. Again, it depends on the application and the requirement, design requirements. So then it will be subjecting to the post-processing of the parts, right? And then you have, once you complete this, and the quality assurance. Yeah, this is either you can use a NDT evaluation or you have a mechanical properties which we need to. But the challenge here is then you have a very limited standards. By ASTM or ISO standards, you can see very few. Yeah, that is what which still it is evolving technology, but hardly you can find some 50 or maybe around less than 100 standards as on date. Maybe another 100 standards may be under development by ASTM and ISO together. So then that is what the quality assurance will come into picture. And then which we have next step is to, the creating a digital twin, right? So that is most important part here. Now we are talking about, so then creating a digital twin, and this technology is very ready to integrate with the Industry 4 technology, right? So that is what, everything is a digital driven system here. unlike your conventional manufacturing system. So you can create a digital twin, right? And then machine maintenance, of course, again depends on type of machine that you are using it, right? And then cleaning up the machine and supply the powders to the machine, so all that, and ensure safety. So this is the complete value chain of any typical additive manufacturing system, right? Yeah, and coming to the design approaches, say if you on seeing this design, one can understand this is meant for a CNC technology, a subtractive manufacturing technology. Though it is a manifold, right? So it is a manifold. So on seeing this design, one can understand this is meant for a subtractive manufacturing process. This design is meant for. Why? Because you have all these 6 phases, and everything is around that 6 phases. You have arranged your say inlet and outlet things. Means your designer might have constrained by the manufacturing say manufacturability of this design. So that is the biggest thing. If at all, if you want to manufacture without changing the design here, so you have the conventional design, so you want to just print it without changing the design, then what is going to the scenario here? We will try to see. And not always, you may be constrained by, say, you are not supposed to alter the designs in some of the situations, right? Maybe it may be a spare part, for example. So you don't have a flexibility to change the design. So in that case, just you can directly say print it. But for example, this may be a 4.6 kg weight. But now you realized, no, you have a huge bulk of mass here. So then your designer thought, okay, this is, and maybe it may be in aerospace or application where we need to weight is a major constraint, right? So then 4.6 kg, just simply by making the bulk into a shell, now you could able to reduce the weight, that is 1 kg, right? So means just you have changed the form here. With a form change, so you could able to reduce the weight, right? And then you have that you may call as adapt for additive, but you have one more step ahead. Design for additive means not only form, so functionality means now you can see you have changed the fluid flow directions in a different way. So where your say it has improved the fluid flow, the efficiency of the system because of your design change, and also the fitment. It's very compact now, the design which you have modified, and maybe by considering the constraints of the AM also you might have tweaked the design. That may be another story. But anyway, so you have changed all 3 F's, means that is form, fitment and functionality. So you have changed. Now you realize, so it is 0.4 kg, means if you see the original design, so now you have only 91% you have a reduction of the weight, right? And not only that, your fluid flow, the performance of the system has been improved, and it has a less space required. It's very compact design, right? So then why I'm talking all this is, so next slide will tell you the story. Okay, so the same thing like a solid block you want to manufacture. Now you try to see the economics of it, right? So what could be the manufacturing cost of this manifold? So if you, as it is without changing the design, if you want to fabricate it on a metal AM machine, right? So metal AM machine, if you want to fabricate it, for example, so if you see the scan time, the hatch pattern, it is 191 hours. Why? Because you have a huge bulk of material here. So means it is not contributing anything towards the functionality maybe. So then unnecessarily it may be increasing your scan time, means your the machine hour rate. So if you say we are going to charge say 2000 rupees per hour on the machine, like say if it is 191 hours into 2000 rupees, that's what which we need to bear, and plus the material cost. The material weight is now 7.4 kg, right? Maybe you can add the material cost, and the service bureau may be quoting this much amount, we want to proceed with this design, So then you might have given the code, and that it is 316L stainless steel. Imagine that is a titanium, so it is much expensive, right? But anyway, so then you have changed it from solid block to the shell block manifold here, the same design. Now you can see it is 36 hours. So you can see how much cost you have reduced, saved, right? So from this design to this design. And further, you have adopted, say, by considering the supports and other aspects of design, aspects of IAM. So now it is only 19 hours. So which you can see how much, in terms of material, in terms of manufacturing cost, right? So that's what, so you always, you have a design, you ensure that it is always redesigned. Why? Because in order to, say, exploit, or in order to get the maximum benefit of additive manufacturing technology. Otherwise, it may be much costly, right? So if you reproduce the same design, so we need to pay heavily, right? So one can understand the design importance here in additive. Sorry for that, something else. Yeah, so if you see, your design freedom is, so your designer is not constrained by the manufacturability, or say, again, you see these, the left side one, the left side design and the right side design. So where your designer might have, say, compromised his innovation or his design based on the manufacturability of the component, maybe targeting to subtractive manufacturing process. But if you see the right side design, so where you can have a better performance of the system as well, you have a lot of design freedom once you are using this AM, right? Yeah, and then in continuation with the, say, injection molding dies, so if you have a conventional, say, the cooling channels where always you drill a straight holes like this, but you have an additive manufacturing system. Your tool has been designed with incorporating these conformal cooling channels, and you try to see the difference between the traditional tool and the additively manufactured with the conformal cooling channel. So you can find a less errors or the defects, and also the die life has been increased. So means you are adding some value to the product. And in a summary, so your manufacturing complexity is free of cost here, right? So whether it is 1x complex or it may be a 10x complex, but your cost remains same. So your manufacturing complexity is always free. Means it may be a cylindrical object, or maybe a topology optimized or a bio-inspired design like this. So you're not going to pay any extra towards this kind of complex design. So once you migrate to additive manufacturing system, right? And the variety is free, right? So imagine that you have all these different geometries. So you try to adopt any conventional method. So we need to write at least those many programs if it is a CNC, right? But here in additive, it won't care what kind of geometry that is, right? So you can, in a single setup, so you can make all these by layer. It won't care what kind of geometry that you are printing it. That is not the case in a conventional, any traditional manufacturing system, right? So your variety is free. and no assembly is required, right? That's what like we are talking about. So the part consolidation. So you can reduce the part count in an assembly or in a sub-assembly. So you sometimes in an assembly you have a less number of parts. Your maintenance is easy, and as well, so you don't have much. You have more parts, more nuisance, but you have less number of parts and less nuisance in your assembly or in your system. And zero lead time, of course, as we know that you see the supply chain in traditional versus AM. So you need only the inventory, a digital inventory, not the physical inventory in case of a traditional manufacturing systems. So you need only the digital inventory like a designs, right? So, and then your logistics is very simple here, like not unlike your conventional manufacturing systems. And unlimited design space. Again, so your designer has come out with out of the box thinking, and then there won't be any limitation for his imagination for your designer, right? So any unlimited design space you can get it. And zero skill manufacturing. Why? Because in a conventional manufacturing process, again, we need to see a lot of things here, but it is something like a push button, but it is not applicable for the metal, but maybe some extent, but the philosophy of any AM, so you have a digital data, and then it is a kind of a push button kind of a thing, right? And you don't require much of the, say, skill in the manufacturing kind of thing, unlike your conventional manufacturing system. And this is a compact, portable, right? So you have now a desktop-based machines, which it can produce a decent size, unless you have a bigger machine and producing a smaller components in case of traditional manufacturing system. But here, your system, your machinery is very compact and less wastage byproduct. Anyway, you are adding the material and infinite shades of material. This is very important, right? So you have a materials, structures you can make with the additive, which otherwise conventional manufacturing methods may not support this kind of infinite shades of materials. Like you have somewhere electronic material, non-electronic material, right? So you can even print them in a single setup, right? So you have infinite shades of material here. And then you have a precise physical replication, right? So you can precisely replicate. So means you have a soft copy, you have a scanner and you have a printer with you. Like you can convert soft to hard or hard to soft, vice versa. Like with a kind of 3D scanning technology, if you integrate with the 3D printing technology, right? Yeah, and then you try to see the data interface, like say like your 2D printer. So any document, PDF or any kind of a form, which is ultimately post-scripting the printer and it is getting printed, right? And similarly, STL, of course, or even it could be 3MF or AMF. So your file or your data is come with a kind of a neutral format, something like this. And STL is basically a triangular mesh data, right? But STL is not ideal. In fact, it is not ideal, right? Why? Because it doesn't support color, it doesn't support material, it doesn't support any texture, yeah. So, but it is not ideal, but still it is going as a de facto standard. The reasons, it's a simplest form. For computationally, it is very simple. Why? Because you need to perform a slicing algorithm as to do that job. But like you can come across AMF and 3MF file formats, which it can even ASTM is trying to make it as a standard format, but still it is not happening. But maybe 3MF, some industries, yes, the 3MF is very well known nowadays. Even it could be in the form of a 3MF file format, you can send it to the machine. Yeah, if you try to see the process plan involved, you have a CAD to STL, STL to slicing, and slice to G code, means you need to fill this with contours, right? So you need to have a scan strategies to fill if it is a laser based system. So this is the typical flow. And other important thing is a part orientation, right? So that's what where you see the other side of the coin. So you cannot get isotropic properties in any AM produced part, right? So that is a major challenge. But again, it will vary the level of anisotropy from one process to other process, one material to other material. Yeah, like, but your part orientation is going to play a major role here in order to match or leverage your properties versus right, your orientation. Then that is one of the design consideration or the design guidelines. And again, you may have several criterions here, maybe a build time criteria, maybe a support material minimization, or maybe accuracy means you want to reduce the chord height, right? So, or staircasing effect, maybe it may be more in one orientation, other orientation. You have you have to do a lot here in order to optimize your orientation of the part. That's going to play a major role here. And slice, of course, slice thickness, more or less, it is a uniform slicing. So all proprietary machines will support only uniform slicing method, but maybe it could be a kind of adaptive slicing, or it may be a region-wise adaptive slicing kind of algorithms, but I am not sure whether proprietary machines will support such kind of, say, varying in the layer thickness between the layers. And the other aspect is support structures, right? So again, the support structure, orientation, it will go hand in hand if you have one orientation, right? So you have a different supports here altogether, right? And then supports, yeah, again, and always you cannot give a general statement that always you remove the supports, but that is not a story, right? So here in the metal, we need to give somewhere the supports in order to have a proper heat conduction in your layers within the layer, or so we cannot outrightly say that always you avoid the supports or minimize the supports. Sometimes it may even useful for reducing your warpage or reducing your residual stresses that has been built up in a particular layer, right? So yeah, so then support structure, of course, we need to optimize. Yeah, how do you do in a design that thing, right? So of course, your software will suggest some sort of optimal usage of the supports, but you have a different criterions here, right? Then which criteria the software has been adopted, we don't know, right? So what is our requirement? So again, we need to say choose a right choice of your how do you tackle this kind of a support structures while designing your AM parts, right? So then if you see the typical, you have a pre-processing of the parts, that's what which you are talking about, anything related to design or your process plan, the initial, this is a pre-processing of the parts, the conceptual idea to CAD model to the conversion to STL and diagnose the STL file. You have some errors in the file. What happened? Yeah, so you have some errors in the file, right? So unfortunately, neither your CAD software nor your AM software, which is integral part of your machine, you don't have a mechanism to check whether your STL file is healthy or not, right? But you may have some third-party softwares like Magix, maybe some other softwares, right? So then here it's very important, if you give garbage in, and you will get a garbage out, right? Whether how much healthy your STL file, that is a big question here. So okay, your file, STL file is okay, then it has been diagnosed, it has been scanned, and everything is okay, then it will be, now you set up the part orientation as we discussed, like what could be the criteria to set up your or fix your part orientation, and generating the supports as well. So then while this is very important, right? If you try to see, we need to prevent the distortion, warpage, curling. So that is going to play a major role, your supports. So then how do you do that? And support overhangs, that is the angle which you have down face, up facing, right? So in that case, like how you are going to do that? And providing the balance to part and easy removal, maybe another aspect. And slicing, as we discussed, it may be an direct slicing, uniform slicing, adaptive slicing, and so on. And generation of the tool paths, maybe again like how your laser or your the extrusion nozzle, your extruder, like your raster scanning, directional scanning, and you have a different patterns. So it is going to dictate your residual stresses also, like which we are going to see maybe upcoming days, like how you can minimize those residual stresses, right? So in order to say, you can do somewhat manipulating with your scan strategies, right? So you have some angle maybe which you can not allowing your residual stresses in the same plane or same layer, so then you are trying to manipulate with your laser strategies, right? And that is what you do in a pre-processing of the part. And post-processing of the part, like as we remove the support structure and you improve the surface finish, and then improving the accuracy, aesthetics, modifying the properties, reducing the porosity, maybe hipping you can, or heat treatment, or mechanical properties you want to, you can do all that stuff in post-processing of the parts, right? And then the topology optimization. But anyway, tomorrow we are going to demonstrate N topology as a one software. So we are going to see how we can design, we can say come out with, so you try to see this, the CAD systems approach, like when it was started, that is during 70s, early 70s, like we used to have a parametric modeling. That was the scenario of your CAD developers used to use. But now you have a generative design, topology optimization, lattice structures, biomimicry or bionic designs, right? So, okay, your designer have a lot of, say, ideas, taking the inspiration from the nature or the biological aspects, or your artificial intelligence. Now it is coming in a big way, like AI generated designs. So it has given tons of, say, generated ideas. Then how do you get manufactured, right? That at the end of the day, somebody has to manufacture that, right? So you have all these the complex designs, complex geometries. So then it's a big challenge for us, even for the AM also, right? Which you can see such kind of a challenges are coming up now. And one way of doing it may be simulation. Why? Because you don't have a luxury to build and you are using a titanium as the material, right? So it's very expensive, and the machine hour rate, as I quoted, maybe 2,000 rupees per hour. Then experimentation, but it's not always possible to do that. And right, you have a lot of scope to simulate, model, simulate your multi-physics, structured modeling is coming in a big way, right? So anyway, so this is some idea, the topology optimized and bionic designs, where you are additively manufactured, AM can easily produce not extra cost. Your complexity is free of cost. That's what we have been talking about, right? So you try to see all these topology optimized structures are bionic designs, right, in the aerospace structures, right? So then it may be, you can see from Airbus, Boeing, all these structural elements, it has been, the weight reduction is the major advantage here. Why? Because more or less, which you are inspiring from the biological aspects, maybe a cell biology, maybe you may be inspired, your designer may be inspired, and reducing a lot of weight. So what is the big deal in reducing a weight? Reducing a weight is a huge fuel saving, right? So even if you could able to save 1 gram payload in aircraft, that itself a big achievement. You see the entire life of the aircraft, maybe 20-25 years. So how much fuel saving, right? That is going to happen. Yeah, and monolithic structures where you can make it integral part of your, say, your fuel injector and the thrust chamber, make it as a single, in a single setup. You can say your AM, it is an Inconel super alloy, right? Inconel 718. So how you can make use of this technology, like say here again you are taking the inspiration from a lattice based designs here. So means you are reducing the weight one hand, and also you are improving the cooling efficiency, means your surface area, right, it's a heat exchanger, your surface area has been increased, and you are going to get that benefit. Means your surface area has been increased, your cooling improves, and also your weight reduction, right? So that's what like companies like GE or Pat Whitney or Rolls-Royce, right? So they are adapting this kind of technology for these kind of heat exchangers, as we already discussed. So the surface area, right here. So your surface area is more, means your designs are inspired by the biology, right? By you are biomimicking the designs, all these heat exchangers. And nowadays you can able to even print in copper. So copper is the best conductor, as we know that. So you have the best designer in the universe, that is none other than nature, right? So where you have your designer has taken the inspiration from the nature or the biology, then you have the best material for the heat exchangers, copper. Yes, you always you can get that benefit here, right? And personalization is a big say, yeah, for my height and weight, my pressure points are different here, right? So, and your pressure points are different, your weight and your body dynamics is different. But your shoe has been designed not considering all these aspects. But now you have a thing here, you can personalize your shoe soles, maybe for the diabetes, for example. Yes, you can always personalize these shoe soles as for the body dynamics or as per the user's requirement, right? So, and also your 3D printed dresses, right? So where the fashion designer might have taken the inspiration from the biology or the nature, right? Yeah, and if you try to see again why it is so popular in healthcare, right? And you can biomimic you have a chest implant or you have a spinal wedge implant. So you try to see your bone structure, the anatomy of the bone. So you have outer is a harder, that's a cortile bone, and if you go inside, it is porous, right? So you have a kind of a sandwich structure here. So you have outside as a solid, and if you go inside, it's much porous, right? So none other than this technology will produce or fabricate this kind of personalized implants, which is mimicking the patient anatomy. In this case, the bone, right? It could be a joint, it could be a bone, or any organ for that matter. So which you could able to personalize. That's what companies like Anatomics, Jimmers, Steiker, right? So they are deploying this kind of additive technology heavily in their medical device manufacturing. And you have orthopedic casts, right? Again, a lightweighting. So whether it is aerospace or medical, right? So lightweighting is always required. Maybe here again, the orthopedic casts, right? And if you try to see your the kind of femoral ball here, so all the weight will come, and that's what you have a solid over there, and you have a cell growth here. So the porous there, right? So none other than additive technology can produce in a single setup. Somewhere it is solid, somewhere it is porous, and that too you can control that porosity, right? So porosity may be a defect if you see in our aspect, but you are creating intentionally a porous structure which is mimicking the anatomy of the patient or the user, right? So that's what where we need to personalize those kind of designs. Yeah, you try to see the topology optimized softwares like OptiStruct or Inspire or maybe N topology. Tomorrow we are going to give an N topology a demo and tomorrow session. AM processes, yeah, as for the ASTM, these are the 7 processes as we know that, and you have a polymers. Again, in the polymers, thermosets are possible through a VAT system or a material jetting system, and thermoplastics are possible through extrusion based system, right? So like that. So you have the polymers and you have the metals. It may be a non-ferrous, or it may be a ferrous, or it may be metal or metal alloy. So all sort of things are available. And ceramics, of course, you can 3D print it. Composites, again, it may be a fiber reinforced or metal matrix, right? So you can always composites. Not only the standard engineering materials class, but even you can functional, electronic, shape memory, biology, food, even the living cells could also be the material, right? That's what a regenerative medicine is all about. Say you cannot do it in a conventional manufacturing method like this kind of material choices. Apart from engineering materials, you have natural materials, or you have even living cells of the human being is also become a material for printing, right? Yeah, I think the previous speaker might touched up all these the feedstock form and then the principles of these AM processes, and maybe a single step polymer, how these 7 AM processes will work, right? Because running short of time, I may be skipping all this. So in the, yeah, metal, even it could be a single step, like your powder bed system or a DED. Yes, you can make it in a single step. But if you talk about binder jetting may be in a 2-step process, or through a material extrusion process you can do metal printing, but that is in a 2-step process. You need to debind, and then you need to sinter, and then you will get a 100% dense metal part. It is possible not only with the powder bed, not only with the DED, you can get the metal parts in other AM processes like binder jetting, material jetting, extrusion process also, right? But not in a single step. It may be in 2 steps. Yeah, if you try to see the developments in VAT, though it started with the epoxy acrylate material, right? But nowadays you can even have a sort of ceramics also can be possible, not in a direct, maybe a 2-step process. Material jetting, yes, here you can see nanoparticle jetting from X-jet. Metal can also be jetted through a material jetting system. Binder jetting, yeah, you can even go with a metal, but as I said already, it's not a single step. Maybe you do debinding, sintering, then you will get a metal part maybe through a binder jetting. And extrusion based, yes, so even metals can also be extruded, right? Like you have a Mark Forge, or you have other technologies where you can even produce metal, but not in a single step, maybe 2 steps. Always sheet metal, sheet lamination process, which you have a sheets or the laminates as a feedstock, and powder bed, anyway, which our course is revolving around this powder bed modeling, simulation kind of stuff. And it may be a laser, or it may be electron beam, predominantly the energy source. And directed energy, it is predominantly for metals, right? And then you have again a wire fed, or maybe a powder blown technology, right? Again, it may be a laser, or it may be a electron beam, or even it could be an arc, or even it could be something else, maybe, right? So which it can be somewhat similar to your welding technology if you try to correlate it, maybe TIG, MIG welding. But anyway, these are some of the materials versus all the 7 AM processes. So anyway, I will leave this PPT, you can have a glance afterwards. So then you talk about the part consolidation, right? So the part consolidation. So why do you want to have these kind of fasteners actually? Is there any need for the fasteners? So if you could able to eliminate those fasteners, so maybe because of some limitation in your manufacturing process, probably you made it several parts and it might have assembled together with some sort of fasteners, right? So if you have a technology which can produce without a fasteners, something like your modular kind of a design, so which we can see only the electronic parts, like it may be a motor or it may be sensors, and rest of that casing can be all your 19 components. Now it has been made only the 4 components, right? So your part consolidation is going to happen here once you have so additive manufacturing technology with you. And the same thing for here, you try to see at least 48 fasteners are there, 1, 2, 3, 4, 5 components. Why? Because you could not machine like this. Probably you might have, they might have done in 5 parts, and they might have assembled it, right, with the fasteners. But like if you have any technology which can produce in a single setup, then why you want to have the fasteners? It doesn't require any fasteners at all. Maybe the limitation in the existing manufacturing processes probably that might have taken place. Yeah, this is a well-known case study. Again, this is from GE, right? And part consolidation, if you try to see, earlier it was 20 parts, and now it is only single part. All your 20 parts, now it made it as a single component like this, right? So then at least you have some 18 nozzles in a single engine. So you have 2 engines or in a aircraft, right? So then what is the biggest deal here? So your inventory has been reduced 95% and weight reduction has happened, right? And durability, 5x times durable and 30% cost efficiency. Yeah, so you have all these advantages. That's what the aero industry looking for, this kind of technology, right? And like Boeing, so, and from the GE 9X engines, and then this is the most fuel efficient engine they are quoting, and 300 parts has been consolidated. See if you take, this is somewhere some diffuser part, you try to see there are 300 components, but all the 300 components made it a single component, right? So then in this way, where you can consolidate your parts. So this is another case study from GE, right? So this is a catalyst series of engine, like 1/3 engine parts of the engine. So the GE is targeting additively manufacture, 3D print it. That's what. But the biggest challenge here is qualification and the certification, right? So why? Because the at least 2 areas, that is aerospace and medical, which we need to get it certified, we need to get it qualified, right? So we should not play with the lives of the people, like where they are going to fly on aircraft, or if it is a implant which it is going to fix inside the body, right? So where we need to get it certified, get it qualified, right? And like FAA, the Federal Aviation Authority, and with ISO, the ASTM, so they are working together to accelerate this qualification process. You try to see this 2015-20. So it's a 5 years they started and they got certified, right? So and if you try to see in Indian scenario, we have a DRDO components, the CEMILAC, there is a one certification agency, right? So yeah, so then the regulator or the person who certifies these kind of components, it is getting certified. Nowadays you have some accelerated procedure to get it certified. Why? Because altogether you are changing the design. It is not a conventional design. So for the conventional design, you might have a certification from the agencies, but now altogether you are in the name of part consolidation, you are redesigning the entire assembly or each and every component in your aircraft engine, but it should be getting certified, right? So, but it is happening in a fast track manner. It's not lengthy procedure nowadays. You have a simplified design. Your supply chain logistics has been reduced because of your additive manufacturing. The philosophy which you are talking about, part consolidation and all, the assembly got much simplified, and your maintenance has been simplified, right? So you have less number of parts, your maintenance cost is less, and your running cost is less. So in that way, so it can be much economical also. And the weight savings and the efficiency, the fuel burning efficiency has been 20% has been increased, and more power even they are quoting. So which we can see all these advantages. Yeah, and then coming to the tooling, the conformal cooling channel, that's what we are talking about. Like say you have a traditional tool, traditional manufacturing methods like a drilling or like any subtractive process. If you can drill only a straight drill, right, channel. But now you have say here you can confine the flow of the fluid around the part that you are going to manufacture, right? So your design, your cooling channel is designed confining to the shape that you are looking at, the component that you are looking at. The cooling stage is the major stage in any tool design area. So 60 to 70% of the cycle time. So you can reduce cycle time here, and increasing the die life, the tool life is also increased, and your cycle time has been reduced. So you are going to get these kind of advantages if you have additively make a conformal cooling channel like this, right? Yeah, this is what you are talking about. You have, if it is a traditional tool, you have a lot of internal stresses, which we can see on the left figure, and the right side figure, if you see, you have all these, the warpage or the shrinkage is minimal in case of your conformal cooling channel, right? And your distortion, shrinkages, all these is minimal. Yeah, and then most important thing here is then how you can design these flow strategies, right? So you can simulate all this. So you can have the zigzag flow, or you can have the parallel flow, or you can have a spiral. You can optimize this. So based on your tool design, so you can optimize this the flow strategies, and as well your cross section of your cooling channels, right? So your cross sectional, say you can try simulate with the different cross sections. You try with elliptical, oval, or you can have a ribbed one, or you can have a trapezoidal kind of cross section, right? So you can come out with the optimal cross section of your conformal cooling channel. Yeah, you see here, this is the conformal cooling channel where you have, say, your tool has been, the cooling channel has been integral part in a single setup. You can complete this. Just you design a tool with the integral cooling channel, right? And your powder bed system, you can print powder to tool in a single setup, right? So you can do all that simulation and design your tool and then print it. And this some of the case studies. Yeah, and then which we need to see, like, yeah, again, we need to adapt the design for additive manufacturing guidelines here to how do you remove the support structure if you have these kind of cooling channels inside, right? So then we need to play with the support structures, right? So and then post-processing methods, then you have some powder particles which it has been stuck inside your cooling channel, right? So which we need to work on that. And then coming to the last part of my presentation, so you try to see the design guidelines for the polymer AM, right? So the biggest challenge could be anisotropy, and this anisotropy is much tedious in polymer rather than a metal printing. But the polymer printing, so you have this anisotropic kind of thing is much tedious. So one can understand the application of the part that you are going to print it, right? So then based on the application, you have moving part, or you have a load which it is falling, there may be tensile compression, right? And then we need to understand the application of that part and each and every feature. We need to identify what could be the critical feature in your design. Then we need to focus, and based on that we need to fix the orientation, right? So why? Because no way you cannot eliminate the anisotropy nature of 3D printed parts. Then the best way is you try to manipulate the parameter like orientation. You try to see how best you can make it as close as, but again considering the application, the nature of the load, and which is the critical feature in your design, right? Yeah, and then you have say a flat area, something like this. So always you try to minimize your the bulk material. Don't allow in a single layer with a bulk of masses over there, right? That is a thumb rule. Why? Because if you are allowing in a single layer, so your residual stress, you have a temperature gradient, right? So where it will go, that heat dissipation may not be happen properly, right? So in that case, the good idea is make it some inclined 10-degree inclination. So then you are distributing that into number of layers. You are not allowing such kind of say the residual stress or kind of a thing not in a single layer, and you are distributing, if you make it 10-degree angle, so you are distributing that into number of layers, not in a single layer, right? So in that way, which we need to say, we need to come out from the say conventional mindset to the additive mindset. Why? Because we need to understand first each and every process and each material different, it behaves differently, right? Then we need to understand, and based on that your design should be modified or should be tweaked or should be redesigned. So until unless you doesn't know about these ins and outs, so you may not become a good design for additive manufacturing guy. Then ultimately we may be blaming the system, right? You have a large warpage or you have a huge say distortion in the parts. Means at least we try to understand how best we can minimize in the design stage itself. Like, can it be minimized? If at all, then how it could be done, right? So in the supports, yes, it's a biggest challenge. Supports, then you tackle with a kind of overhang angle, right? You have some thumb rule, 45-degree. You try to manipulate with those kind of say and then the area also making a lot of difference here. So then so whether the support material can be given over there or not, then how do you tackle that, right? So all these which we need to understand. So then you can become a very good design for additive manufacturing guy, like which we can, otherwise you maybe end up with some defect in the part or some build failure may happen ultimately, or if at all, if your fabrication is succeeded but maybe some defects in your part. Yeah, and then we need to understand the minimum size of the feature that we are going to realize. That will vary from process to process, of course, and material to material. Say you have say you see the thickness, it may be a 2 mm thick, the left extreme, and 4 mm, 6 mm, 8 mm, 10 mm. And if the thickness is varying, so which we can see the minimum size of the feature that you are going to realize. So that is getting reduced, right? At the moment you increase the thickness of your sample, so you may not be able to realize the smallest feature, or it may be a slot or a hole or any feature for that matter, which we need to understand the constraints of the each and every process, right? So then say you maybe designed this part, but we don't know like which machine or which material you have targeted, what kind of process. Why? Because here the challenge, all 7 processes will behave differently, right? So you have a different energy source and you have a different physics involved, right? So altogether it's a different, you cannot generalize. That is the biggest challenge here. So if you talk about conventional manufacturing process, it is not the case. But the challenge here is each technology or each process behaves differently, and within the same process, each material will behave differently. That is the challenge here, right? That's what which we need to understand. And anyway, you have some kind of always don't let any bulk masses in your design. Always you try to the chop out the material, but don't let until unless, then you should not, you need to understand the application and the other aspects also. By considering that also, just like that, you cannot say that, so my machine could not do this one, then I can change my design as I wish. No, right? So then we need to balance that also, right? So you should not compromise the functionality. In fact, you are saying that you are adding the value to the product as you are changing the design. So we need to keep in mind all this, right? So accordingly we need to do it. And then you have a salt shaker holes, like especially for the VAT system or powder bed system, right? So you have a hollow part like this if you made through a powder bed system. So then you have stuck up with the loose powder inside, and it is a vat system. So you have an entrapped liquid inside of your hollow feature of your part, right? So then we need to evacuate it, or we need to evacuate that material inside, right? So for that also we have some kind of a guidelines to be followed, right? So then yeah, that is about some polymer design aspects. And coming to metal, so I will try to give some design aspects. Maybe this conference is all about simulation, modeling. Yeah, that to metal, targeting to metal, powder bed based metal laser, with a laser it has been targeted. So I will try to give some design guidelines or some considerations which we can, and then energy density. I am assuming that everybody knows about this powder bed system probably, right? So you have an energy density that is going to play a major role here, right? So even though it is a 100-watt a laser machine, so which we have only a 100-watt laser machine, but we have successfully done titanium, we have successfully done aluminum, we have successfully done cobalt chrome, we have successfully done 17.4 pH. Then here the trickiest part is how do you play with the parameters? But it may take some longer time. You have a dual laser, or you have a say 500-watt laser. I'm talking about powder bed, not DED, but DED laser rating is different. So I'm talking about only powder bed system, right? So then you can play with the parameters, like, so you try to see the energy density. It is powered by scanning speed times hatch space times layer thickness. So you try to manipulate these parameters, like which you can, right? So anyway, the biggest challenge could be a lack of fusion pores, right? And we have an expert here. Anyway, the conference is all about. But anyway, honestly, I am learning a lot from this course. So then how do you tackle that? Maybe through your microstructure manipulation, or through the kind of tailor making your properties, right? And minimizing these defects. So you try to say balance this, you minimize these, and at the same time you are trying to improve the mechanical properties, or like, so you're going to do that, right? So but anyway, so the laser absorbability, that is going to play a major role here, right? So you have a different material, the photon absorption is different from material to material, right? So anyway, so I'm not going into the deeper aspects of that. So you have absorbed energy, scattered energy, reflected energy, so all that. Yeah, the major part here is like how you are going to say make use of your scanning strategies here, right? So not allowing the residual stresses that is it has been accumulated at a region or a layer, right? So for that reason, which you are trying to alternatively, or you are varying the laser paths with some inclination, right? Some 40 degree, 45 degree, 30 degree, something like that, right? So then, which we need to do all this. So say you manipulate these parameters in such a way that maybe residual stress, maybe any sort of thing that we are working. And then other one is unsupported angles, so like your polymer, and here also. But this is very tedious here. Why? Because polymer, it's a low melting material, but it's high melting, and that too you have, it is a powder bed, always you have a single material. You don't have a choice to introduce other composition or other material, but always your powder bed, you have only single material, right? And also if it is steel, and your support is also steel, right? And then your conduction, right? It's going to play, anyway, we have an expert here, like which we are going to discuss all that aspects, conduction, all that thermal thermomechanical modeling of it. So anyway, your unsupported angle is going to play a major role. If you are not following that thumb rule or that guidelines, so with supports, then you are trying to build, and ultimately you may not be succeeded in your build. And unsupported overhang also, which we need to understand what could be the typical value that you, without an overhang, you can produce. If you are trying to produce, or you are designing above that threshold value, but obviously you may not be able to realize that feature, right? And similarly, here also, which you can see 1 mm, 2 mm, yeah, it is coming properly. But if you see above 2 mm, maybe 3 mm, 4 mm, 5 mm, so you could not realize. So these kind of features. Yeah, and the effect of residual stress that we have been talking about, you come out with different the scan strategies, maybe with hatch, mander, or maybe stripe, or maybe a chessboard. Why? Because you try to see like how your interaction of the laser with the powder, right? So then, which we can, some extent, we can manipulate, not letting these residual stress in a particular region, or you try to vary the scan strategy in such a way that we can reduce these residual stresses. And another one is uneven thickness of these features, which we can see. So you follow the thumb rule, or the unlike like your injection molding also, like which we have some thumb rules which we need to follow here also. Always you use a uniform thickness, but not varying thicknesses. Maybe again it will create a problem here, right? And of course the stress concentration, yes. So the stress concentration here also, which you can see, not abrupt kind of the features, like you have some filleting or something like that, which you can minimize this kind of a stress concentration of the parts that has been built, right? And here also uneven thicknesses, maybe it will create a lot of residual stresses and the deformation, right? So then you try to see the uniform thickness across, and then always following a filleting of it, and then horizontal holes. So the horizontal holes, which you can see right from the 2 mm, 3, 4 mm, 6 mm, 6 mm, 8 mm, you see above the 8 mm, which you can see some teardrop kind of, even though you are trying to print it in a circular one, but it's not realized. So in that case, what is the design guideline? Maybe if it is more than 8 mm, maybe slightly you change your design, maybe to the elliptical hole or maybe a teardrop. Anyway, you are trying to build it as a circular, and you are getting a teardrop kind of a shape, and design itself you change like a teardrop. That's what you can have, and a diamond shaped holes. And the part positioning in your build platform, right? That's going to play a major role. I'm talking about the powder bed. So you have a roller or a recoater, right? So the roller or recoater, so don't put in this orientation. You have a huge force, or like you have a huge contact area with your roller with the part, right? So then you make it some 45-degree angle like this, right? So then you can minimize such kind of problem. So like that, which we need to, and don't line up like this, right? So don't line up these parts like this. You make it alternatively. So then, which we need to follow some general guidelines for positioning these. And other thing is like sometimes you're going to get a recoater, a blade will hit your the parts, right? So then the recoater will badly damage your part, right? Which we need to take care of that. And if what could be the tallest part in your build, and all that we need to consider, right? So in order to, if you consider all that, so you may not be end up with say damaging your printer or damaging your part. Yeah, and you try to see these design constraints in AM. you are trying to make some support wall like this, and you have a different AIM processes, right, from the FTM, the fuse deposition, and then stereolithography, selective laser sintering, material jetting, binder jetting, and the direct metal laser sintering. So you try to see what could be the minimum size of the wall that you can realize, right? So it is varying from process to process, obviously, right? So if you see extrusion based system, yes, you have a nozzle. Nozzle you have some diameter, right? But you have a the VAT system like stereolithography, you have a light, right? So their energy source is light, and you have the what could be the spot size or the light thing, or like selective laser sintering, again you have the laser, what could be the laser spot size. It's going to dictate your features like a support wall or unsupported wall or any overhang, right? And then you have embossing, engraving features and horizontal bridges and minimum size of the hole that you can realize. So it is varying from process to process, but we need to understand, without targeting a particular technology, and you are designing this, and we need to understand, say for example, if you take the minimum hole size that you can realize is 2 mm in case of extrusion based system. So if you are designing a 1.5 mm hole, obviously if you are trying to print it on extrusion based system, it won't realize, right? So then we need to understand these constraints. Each and every process will have some constraints, so which we need to understand. We need to avoid such a kind of a situation where you could not build it, or there's some build failure. So because of the reasons, maybe you may not be followed the guidelines, the design guidelines properly. And you may have other features like the moving parts. So what could be the clearance between the moving parts? So again, it is varying from process to process. And you have escape holes. Just now we have discussed some salt snaker hole, like which it maybe, then what could be the size of that escape hole, and minimum size of the feature, and pin diameter, tolerance, all these it will be varying from one process to other process, which we need to understand, right? And you try to see universities like Purdue University, so they have come out with some kind of design for additive manufacturing matrices, like just you can scan your design, and it may be it's going to give some score. It will tell you whether what is the success rate of your part that you can print. So then there will be some score. Based on the score, you can take a call, like whether we need to design a particular feature, or you can go ahead without difficulty. So based on your score, so that is you see the matrices for that: complexity, functionality, material removal, unsupported features, thin features, stress concentration, tolerance, geometrical exactness. So they have devised a matrix by say categorizing various parameters. So once you run through your design, so it will tell you the failure rate of that particular design. And build simulation, anyway, I'm not an expert, I'm also learning. So you have a multi-physics, multi-scale modeling. So in this case, you are modeling distortion, residual stresses. Anyway, tomorrow we are going to see how we can predict this kind of a thing, and then if at all, if you do compensate it, how do you get compensated? Distortion compensation and optimizing the support structures, and minimum risk of printer damage, recorder damage, which previously also we were discussing, minimizing the number of build tryouts, and predicting the impact of post-processing like heat treatment, heaping, or support removal. This is the transport or the dissipation of your heat. So you have a huge, what you call, so the thermodynamics involved, or the heat transfer, the kind of a transport mechanism here, like, so you have a heat conduction, heat radiation, right, and heat, you have evaporation, and you have recoil pressure, right? So anyway, we have another expert who is expert in this area, then we'll listen his lectures maybe upcoming lectures, maybe tomorrow, day after tomorrow, exclusively on that. So you try to see the simulation softwares. Anyway, which we are going to expose you on a 3D expert software, that is 3D systems metal machine, that is powder bed system. This is a 3D expert, or ANSYS additive print, and even from Hexagon there is a SimuFact additive, and Make in India. Recently I met some people from Indian Make. They're already they're about to launch commercially this kind of a simulation software for powder bed system. So you have a lot of, but still this is upcoming area, but there is a huge potential. Again, it's a gray area, right, which we can see from his talk also. There is a huge potential we need to tap, or we need to work, right? So several aspects of these simulation, modeling and simulation of this powder bed system, right? So though you have some proprietary commercial softwares, but they may say that it will work for only for their machines, but how closer that data, we don't know, right? Then how, we have other softwares also under this category. Fabrication challenges, so any part, whether you made correct or wrong, that will dictated by your standards, right? So unfortunately, you don't find much standards in this space, right? So again, try to see the standards, maybe design related standards are there, and terminology related, and fabrication, feedstock related standards from ASTM and ISO together. But it's very few. You have a very few standards, but still under development several standards. That is the biggest challenge. And if you try to see the part quality of any typical powder bed system, so it at least 200, 300 parameters, it is going to affect. Like even from the previous lecture also, we came to know that there will be a huge impact or effect on the feedstock powder, right? So which we can see the material related chemical properties or powder characteristics, metallurgical properties, rheological properties of your feedstock material, right? And then optical properties. So you have a material related challenges which we need to address. And AM machine, of course, machine which we need to some extent we discussed, maybe mechanical components, maybe gas supply, maybe inerting, and your kind of the AM system related, and part related, of course, that is a design for AM, which you can work on it and you try to minimize those sort of challenges with a design. But everything you cannot do a design during the process, or during the feedstock preparation, or during interaction of your say energy with the feedstock, right? And you have operator pre-processing, yes, that is during your say slicing, during slicing, or maybe during part positioning, part orientation, setting up of and the process related, of course, process parameters, right, from the layer thickness, you have a laser power or energy density which you are talking about. So you have those process related parameters, and of course post processing at the end. So you have the support structure removal or heat treatment, surface treatment. So it's going to affect a lot, right? So we cannot say that, and you have these many combinations and permutations, like, so then how do you detect, then how do you say tackle or targeting to a particular thing and saying that, oh yeah, I have done, say without any error I have done it, right? So yeah, okay, we'll so let me summarize what we have done so far. So quickly introduce this AM and design approaches in AM, like right from the direct AM, or you have three approaches which we discussed, right? And DFAM finally, design for additive manufacturing approach. Topology optimization, bionic designs. AM processes, you have a different constraints. Each and every process will have different constraints. And part consolidation, yes, you can very well use this technology for part consolidation applications. And conformal cooling channels, yes. And you have a different ball game altogether for the polymer to metal, right? And build simulation challenges, that's what this conference, like you can concentrate much on modeling simulation aspects and how you can minimize your errors or the defects, right? And anyway, you are coming to the lab. These are some of the facilities we have. We have a DMP Flex metal AM machine anyway. Day after tomorrow, we are going to give. And even we have a material jetting system that is from ProJet 2500 plus. And we have two FDM based machines. And then, of course, we have a desktop based polymer machines and two scanners. And the softwares, exclusively softwares for medical device design and like Mimics, Magix, Thematic, 3D Sprint, 3D Export. These are the AM softwares which we have. Yeah, that's all from my side. If you have any questions. So then, if you don't have questions, then we'll call the day today, and then tomorrow 9:30 you are going to start. Okay. Yeah, 9:30. Yeah, then we'll call the day today, right? So thank you for the patient listening. Yeah.